Okay, so the last part of your persistent homology lab would be, okay, for this classification, we're going to use data that we get from this equation. Right? This equation is called a twisted map dynamical state equation. That would produce x and y values here, the point cloud, with different kind of structures. Yes, so for example, when there is one parameter, so-called r, this parameter with different setting, it can create a different kind of data, a very different kind of data. For example, when r 4.3, you get such a data where like you can see like a small two holes in between the data. Yeah, and if you remember the first one of the few first slides when I started to teach persistent homology, this slide here, you see the first one is in all these three point clouds were actually produced by the dynamical state twisted map equation. Yeah. As you can see, the title, it says R is 3.5. See, as you can see, if R is 3.5, you don't see any holes in there. Whereas when R is 4.3, you get to see like two holes. And when R is 4, it becomes like one hole, right? So with different values of R, right, you get to produce different kind of point cloud, yeah, with the different kind of structure. Okay, so we're going to use that equation and this equation to create a different point cloud where R would be our label. Yeah, R would be our label. So we are going to create like 50 point cloud with R with let's say for example R 4.3, we're going to create 10, R maybe 3.5, you're going to create 10. So we're going to create such a data for 50 point cloud, right? R being the label. And of course, once we produce the data, then we are going to run persistent homology with RIPS. I think alpha complex, since it's a two-dimensional space, and then we will get persistence diagram, and then we will convert it into a persistence landscape. Yeah, persistent landscape, and then use persistent landscape to run classification. Okay, so as you can see here again, the persistent landscape for different R has very different structure. Yeah, for class 0, so-called class 0, we define class 0, where R being 2.5, we get such a persistence landscape. Whereas for class 1, R equals to 3.5, somewhat different. Class 2, R 4.0, very different. Class 3, R 4.1, for class 4 R 4.3, and we can see a different structure. So from here, we can in fact clearly see that we would be able to use the information, persistence landscape information, to differentiate the labels, right, in order to do classification. Okay, now let's do that. In order, before doing it, let's see how we define our framework. Right? Again, for class 0, R 2.5 until class 4, R 4.3. For each class, we create sections. So we have about 50 point cloud. Yeah, for each, all this 50 point cloud, we are going to extract persistence, and we're going to produce persistence diagram. Right? Once we have persistence diagram, we're going to shuffle it and split it into test and train set. So then we're going to do a little bit of processing before doing TDA. First of all, of course, we don't want the infinity. So we're going to remove infinity and we are going to normalize the persistence diagram, and then we're going to use a number of signatures, number of vectors, persistent landscape, persistence image, and then we are going to maybe use a number of we're going to use pipeline actually to do a number of experiment using different kind of estimator, yeah, different kind of classification, support vector classification, as random forest, and see which one suits the best. And then of course how would we do it would be you'll be using hyperparameter tuning via grid search cross validation. And then once we find the right tune, we will then create a model, then try to feed in the test data set in order to see how accurate it is. So for average, in average, just using this 50 point cloud, just using 10 for each point cloud, we get to like up to 80% of accuracy. Okay, so I would now go to the Python code and show you how to do it. Okay. Now this is the Python code to do the classification of twisted map. Okay, so of course first part we bring in GUDHI and GUDHI, and this is the equation. Yeah, so we're going to create 1000 points for each point cloud, and of course R would be the so-called parameter that we are going to tweak to create labels. Okay, so this is how we run the equation point cloud. So we have X values and Y values. Okay, and for example, yeah, so for example, for R equals to 4.1, so you get to like you get to create such a structure, this one whole, right? As when you see like maybe 2.1, you get to see different structure. Yeah, so with just by tweaking R, we get to see very, very different kind of structure. Okay, so of course, straight away I'm using alpha complex since it's just two-dimensional space, can create the persistence diagram, right? And of course, you can just then once we have persistence diagram, you can push it and vectorize it into persistence vector, persistence landscape. So I'm just using H1's information, Betty 1. Yeah, by all means, you can also use Betty 0, but I'm just using Betty 1, and this is how the landscape looks like. Okay, the first tree landscape looks like, and this yeah, I just did this example. Maybe I'll do 4.3, R equals to 4.3. And there you get to see again different structure. You can always run and then make another persistence landscape. Okay, so this is how the persistence diagram looks like. Now, roughly you get the idea of what is this data about. And again, we're going to create 50 point clouds, and R will be our, yeah, these are the R's. We're going to create different R. R will be our label. We're going to for each, we're going to create cloud. Okay, so I'm just going to run in a loop, yeah, the for loop for, so that based on the number of class, yeah, for 2.5, 10 point cloud, 3.5, 10 point cloud, until 4.3, 10 point cloud. So each point cloud, right? So I simply plot it so that I get to see visually what's happening. And then of course, after plotting it, I'm pushing into persistent homology alpha complex. I'm creating persistence. I'm extracting. Yeah, I'm extracting. I'm extracting the dimension 1. I'm keeping it into DGMS. Okay. So once you run, you get to see so many. Yeah, different kind, 2.5. Of course, you will see 2.5, 10 point cloud. You see different time, you get totally different point. Yeah. If any different time you run, you get different point cloud. It's very random. That's why it's called dynamic state. Okay. All right. So we drop it in. Let me show you. So you're going to see 2.5, 10 point cloud, 3.5, 10 point cloud, 4.0, 4.1. So all of a sudden 4.1, we have such a point cloud. It's not wrong. Rather, it is due to the dynamical state of the point cloud. Okay, there you go. Right. So now we can check, yeah, how many that you have created, the length diagrams. So you have like 50 diagrams. Of course, we kept out of the diagram. For example, the first diagram has this point clouds, H1 pairs. Again, we just extracted H1 pairs. All right. And we get to see the labels. Yeah, the label. Class 0 representing 2.5, class 1, 5, and so on until class 4. Okay, these are labels. Now, we are shuffling it manually. Yeah, we're shuffling it like manually. So where we want like 20% our data, test data, and then the rest 80% for testing. We're doing a permutation. Yeah, and just to shuffle it. And then we're going to extract 20%. Yeah, 0.2, 20% out of it. And then the rest going to go for train. Okay, so 0 to 10 for testing, and then the rest 40 point cloud for training. Okay, so all the trains and train labels, test labels, train diagram, test diagram, as such. Yeah, so all these H1 pairs, it's not persistence landscape yet. We are yet to vectorize yet. So this is a permutation if you want to look at. This is the test set you have to look at. This is the test sub. Yeah, once we do permutation, we choose 10. And then this is one of the train diagram, train persistence diagram. We can always plot it and have a look at it. This is how it looks like for the first diagram. It has been, as I said, shuffled. Okay. Now, next thing is to create the pipeline. Yeah, create the pipeline. So in sklearn, we have the pipeline. We're going to use min-max sklearn's pipeline. We are going to use support vector classifier. We are going to use random forest classifier. We're going to also use k-neighbor classifier. Okay, so our pipeline will be first the diagram. We're going to remove the infinite, the infinity sign from the diagram, right? And then we are going to do min-max scalar, and then we are going to do vectorization, and finally we're going to do classification. So that is how our pipeline is going to be, right? So whereas the parameters are, these are the tuning part. Yeah, whatever that you want to experiment that you think that might suit and give you the best result. So the first tuning would be, I want to use the scalar. Yeah, I want to scale it using min-max scalar. So scalar is true. And TDA, I want to use persistence image. Okay, in order to vectorize a persistence diagram, I'm using the resolution would be 5566. Persistent image resolution. The bandwidth would be 0.01 to 1, and then the next one is 1 to 10. And then the estimator, I'm going to use support. This is one setting that I'm going to experiment. The next setting, I'm going to use persistence image as well. this time around, I'm not going to use min max. I'm going to use also random forest classifier to do it. And the third one, this is the landscape. Yeah. I'm going to use each strip and lambda going to be 500 points. I'm going to use random classifier. The next one is so-called bottleneck distance, where you'd be able to collect distance between two persistence, right? This function, what it does is that it would be able to compute distance between two persistence diagram. Yeah, and then after that, we're using k nearest neighbor to compute and see whether you'll be able to classify properly or not. Okay, these are the experiment setup. All right. So next is in order to look at our pipeline, you can call set underscore config from sklearn and just put display diagram. You get to see your pipeline. So first is the diagram represent diagram selector, and then diagram scaler, and then persistence image. So here TDA, type of vectorization you want to do, and then finally what type of estimator you're going to use, right? So it will choose the parameter here, and then you run. Okay, so next, so using grid search CV and cross validation, your pipeline, and then your parameters to test, and then cross validation. How many fold you want? You want 3-fold and 3-fold. So we're going to break data set into 3, and then you're going to test each by each and see which one is the best outcome. Right. So once you get that, you get your model. Yeah, you get a model. So your model is ready to run, and then model.feed train tables. So it will take some time for this to run. Once it's ready, then you get to see best parameter, model.best parameter. So estimator for me, it was rainforest classifier. And of course, we do mix min max classifier. And then the TDA type, TDA with persistent length, solution of 500, which means it chose this one here. This tend to be the best among the rest. Okay, and then just for example, if you have like a different birth and death pairs, H1 birth and death pairs, so you can straight away put a model.predict, and it will give you, for example, it says this one array 3. Array 3 means this must be class 3. Class 3, I think, is 4.1. R is 4.1. Okay, so you can check like accuracy. So for example, the accuracy has dropped here to 0.6. Yeah, quite low. And then okay, you can just again train. If you look at the train accuracy and then test accuracy, so test accuracy is kind of like very low, right? Maybe due to some reason. You can always run again, and I will have a look at it. Let's run again and see. Maybe because of this sort of data where it can be very chaotic, yeah, due to little change, little randomness, the whole outcome is very different. Okay. Example, let's run again and see what sort of accuracy we are getting. Usually run like 10 times, and then only then you report what is the average accuracy of this data set. That would be a better way. Yeah. Okay, so this part here we are finding for the best tune. Okay, done. Just 6.8 seconds. So the estimate. All right. Not much of not much of changes again. Probably I should restart and run again. Maybe we got stuck with the same data set. Rerunning again the whole thing. See, this time around, the second time around, you get like 0.7 accuracy. So maybe you want to run like 10 times and see what is the average accuracy that you get, and then report. Yeah, so that's all. So I hope that you can now continue with your project, and hopefully you'll be able to complete it, and I will be able to see next week. So wish you best of luck. Thank you.